Cool. Well, welcome to hurricane season, at least for us right now. It's September.
Yeah. That's right. And I wanted to get into, I don't know why I asked you to talk about this today, Zach, but yeah, I wanted to talk about the physics of hurricanes. I think they're pretty fascinating, just the scale and the just energy involved. Yeah. And I think some physics is pretty interesting to make hurricanes happen. There's a lot going on.
Yeah, well, and it's pretty relevant at the time of recording. Are monsoons cyclones?
So I had to look that up. I don't think so. I think monsoons are just storms, but there are different names for different types of storms in different parts of the world. But a monsoon is something different than hurricane.
There's no rotational.
Right. Yeah,
monsoon.
so I think cyclone is just the big term for like any rotating storm. And then you got hurricanes in the Atlantic and the northeastern Pacific. So like basically around the US, kind of Canada. And then in the northwestern Pacific, so like Japan, we have typhoons. Then cyclones is, there's like a longer term, that's the big general term. And then like cyclone is South Pacific and Indian Ocean. But the longer term is like cyclonic tropical storm or something like that. Like
that makes sense, right?
Term.
Yeah.
That's the full term for all of them. So hurricanes in the Atlantic and Northeast Pacific. Hurricanes basically like hit the U.S. Typhoons hit Japan, and then cyclones hit, I don't know, Indonesia and India.
Philippines, I think.
Philippines, yeah. So yeah, all the rotating storms, those are them. And then the monsoon is something else. That's just like a big down storm. Big downpour of rain.
Right. So yeah, I mean, I guess that's why it's relevant. It's a good reason to talk about it.
Right. Yeah. So I guess it popped up somewhere in my feed of different things, and so I thought it was interesting. Mainly, I wanted to get into the rotation part, but there's also a lot of like thermal energy stuff that's kind of cool, like how much energy it has in it, like stored, like ridiculous numbers. The thing I read, I think, was like 70 nuclear bombs going off per minute, I want to say.
What?
Like
wow.
That's the like power output of these things. And one storm contains more energy than the entire human race has used ever. Like just that's the energy output of these things.
Wow. Okay. I thought I saw like not quite that much, but that's insane.
Right.
Like how do we harness that?
Yeah. Put up a bunch of wind turbines, and then there's no more hurricane. We have a bunch of electricity.
Yeah. We just have to engineer the crap out of them.
Right. Yeah. So here's the quote. Scientists estimate tropical cyclones release energy at a rate that's equivalent to 70 times the world energy consumption and 200 times the worldwide electrical generating capacity. So like the rate that people consume energy in the world, a hurricane releases 70 times that at that same moment. Like in any moment of time, we consume energy, and then the hurricane does 70 times that.
Yeah. So like, yeah, on average, we're using one human amount of energy. I don't know what you want to call that, one esplee of energy, and the hurricane is using 70 times that on any moment. Wow. Okay.
Yeah. So it's equivalent to exploding a 10 megaton nuclear bomb every 20 minutes. So that's the nuclear bomb comparison.
Wow.
I was off by my per seconds, but still 10 megaton nuclear bomb every 20 minutes. That's how much energy hurricanes put out.
Yeah. Okay. Well, that sounds like a useful thing we need to tackle. Let's get on that and harness that
Just
energy.
Lasso a hurricane.
Yeah.
What was the lasso, the tornado thing? Was that a Pecos Bill? Is that who it is?
I have no idea. Wait, kind of in the back of my head.
Bill tornado. Yeah, Pecos Bill. He rode tornadoes. He lassoed tornadoes.
What does that even mean?
Yeah.
Like he'd get his broomstick and like hop on and get that pretty?
No, it was like a Paul Bunyan type thing, like some really big guy, like huge human. Obviously fictional character, but yeah. I remember it from like cartoons.
Cool. All right. Well,
so we'll get Pecos Bill on the hurricanes now.
All right. Yeah. Yeah. Because it's more, he's going to be able to get more energy out of it.
Right. So where does that energy come from? Like, obviously we have some conservation of energy rule we have to obey. Like, we're not detonating bombs and generating hurricanes. That energy is just sitting there somewhere, and then we get hurricanes to move that energy around. But where did that energy initially come from?
Right. Well, so like when I was looking things up, maybe you have more details than me, but I kind of saw that, that there's kind of like the three components to making a hurricane are a storm. You need, some version of a storm already. You need warm water, I believe. And then you need to not have shear winds. And then those three things combined can potentially generate a hurricane.
What's that third point mean? I don't really know it. Not having shear wind. Okay, go ahead.
Yes. So what it means is, a hurricane's spinning and it's this giant, like, I forget how tall they get, like higher than commercial airliners fly, is like the height of a hurricane. And what can happen, and there's air flowing from the bottom to the top and it kind of sinks back down and you get this loop. Mm-hmm. If you have really strong winds blowing one direction, let's say east at the base of the hurricane, and really strong winds blowing west at the top of the hurricane, it'll kind of disrupt that circular flow pattern, and it can actually just tear the hurricane apart.
Okay. So like top to bottom shearing, like don't have that happening.
Yeah.
Okay. Got it.
And that was kind of like the three things I saw. So I don't know if what you're getting at is the warm water part, or if there's something else before that I'm not.
I think it's
aware
the
of.
warm water part is what I'm getting at. Yeah, like the sun warms up the ocean water gets warm, and that warm water has a ton of energy in it, right? So like the ocean being warm is the source of the energy. Yeah,
I mean, water. Okay, well, first off, I like to point out whenever this comes up that like all energy, it's like I feel like you can trace any energy back to the sun at some point, right? So it's like it always comes from the sun, but
except geothermal.
Yeah, I guess that's true. Although you could say, well, it was from some star that exploded at some point, and then that stuff collected.
Sure. Okay,
depends on how far you want to go back, but yeah, maybe not our sun,
right?
But yeah. So like, I mean, just water itself can hold a huge amount of energy. I remember learning in high school, I think it was, that there's communities in maybe Canada or Alaska, I want to say, where they'll put a large container of water in their house. Mm-hmm. And when it gets really cold, that water will freeze. But when water freezes, it goes from a high energy state to a low energy state. So it gives off energy. And where does that energy go? It goes into the house. And so it actually, like the giant container of water freezing will keep your house warm.
Right. Right. Yeah. If the water wasn't there, all like the energy of the house would be lost to whatever's cooling off the house.
Yeah.
Instead, it cools off the water and the house stays somewhat warm. Not as cold.
Yeah. I mean, or if you've ever just like put some, a gallon of tea out in the sun for a little while, and then you like bring it back inside, that thing stays warm for a long time.
Mm-hmm.
So like,
yeah. So all this energy of the ocean, and I should say like the surface of the ocean, really, because that's what's in contact with the hurricane. That energy is released. The water evaporates and turns into water vapor instead of liquid water. And what that does is it cools down the surface of the ocean, but then the air is now warm because it has this energy that was released from the evaporation of the water that's stored now in the air itself. So the air warms up, and we know warm air rises. So then all of a sudden we have this upward moving air. And what that does is the upward moving air draws in air from the surrounding areas of the surface of the water, right? So at some place there's a bunch of upward moving air. Next to that is a place where there's air rushing in to fill in the empty space that the upward, like if there was no air to the side of it and the air just went up, what would it leave behind? Nothing, like a vacuum, right? So we need air to fill in that space. So we all of a sudden have this like sideways moving air filling in the place where the upward moving air just left.
Yeah, so you get kind of like a low pressure zone from the air moving up.
Right, exactly. Critically, we have a low pressure area. And then that low pressure, lower than the surrounding area, since it's lower pressure, it's kind of like sucks in the air from the surrounding areas.
Right. One thing I wanted to touch on is just like a semi-intuitive way of thinking about evaporation and heat transfer, energy transfer. Mm-hmm. And if you've taken a thermo class or, one of your lower div physics classes, like you probably, I've already heard this, but if you haven't taken those classes, like evaporation really is just when we say something is, 50 degrees, or that seems kind of cold, when it's like 90 degrees, water, we're not talking about like everything in it is exactly 90 degrees. Like on a molecular level, it's all moving at kind of different random speeds. And some molecules have, a higher energy and some molecules have a lower energy, but that kind of averages out to a thing that we say is temperature, and that's 90 degrees. But what can happen, right, is that the higher temperature molecules that are moving around, if they're near the surface, they can just leave the surface if they have enough energy. And so they carry that energy away from the water, so the water gets cooler because it lost like that molecule and that kinetic energy. And then the air now is getting warmer because now it's gaining that sort of energy. So that's kind of what's happening at the surface of the ocean there. So you have these molecules that are moving fast enough that they get to leave. So the ocean drops in temperature, is what you said. And then the air gets a little warmer because of the water that's moved into it.
Right. Yep. Yeah, exactly. So keep what I just said in mind about the low pressure kind of like sucking in the surrounding air, because we're going to come back to that in a little bit. But I want to talk now, like we haven't gotten to like how the hurricane actually starts rotating. And to do that, I want to like just start by thinking about rotations in general. And in particular, thinking about rotating reference frames. And what I mean by that is we normally think of your room as you're sitting at your desk or in a car. Let's not go to a car. Just sitting somewhere. Like this we would consider non-rotating. We would consider it an inertial reference frame. That means it's not accelerating. It's not spinning. Nothing like that. Now, we're technically on Earth, which is rotating, which therefore is a rotating reference frame, really. Even though we don't treat our house as a rotating reference frame very often, sometimes we do need to worry about those effects that come about when you're in a rotating reference frame. And to start, I think the best place is to imagine like a playground merry-go-round, which is the typical physics demo. If you have one of those near a classroom and you're a physics teacher, go out to that thing and play around with it. And it's such a quick way to demonstrate this like kind of complicated phenomenon, but I think everyone's experienced it. So if you picture yourself on one of those playground merry-go-rounds, like the basically big platforms, like, I don't know, what would you say, 10, 15 feet across?
Yeah, something like that.
Yeah. And you get a bunch of people on it and you push along the outside and you all hop on and the whole thing spins. That's what I'm talking about. So imagine the thing spinning and you're sitting across from somebody on that merry-go-round as it spins, and you're holding a ball, and you throw that ball to the person across from you. What you're going to see is that it doesn't hit the person directly across from you, even though you threw it straight at them. What happens is the second it leaves your hand, now the whole merry-go-round is rotating, but the ball wants to go in a straight line to somebody outside the merry-go-round watching, imagine a camera from above,
right,
it's going to see the ball go in a straight line. But to you in the rotating merry-go-round, that ball curves a lot, right? It's just going to like dive out of the way of the person that you threw it to. So that's what we mean by when you're in a rotating reference frame, you got to treat things a little differently and be careful about directions that you expect things to travel.
Right. One way I wanted to add, like, you can think about this is you could play catch with yourself if you're on one of these. So like if you imagine watching somebody, so you're the person standing on the ground. When the person on the merry-go-round throws the ball, it's just going to go in a straight line. So, they're going to be, let's say they throw it when they're facing north, it's just going to keep going north the whole time. But you can see from, like, if you're sitting on the ground, you could potentially imagine the situation where maybe they're directly south, they throw the ball north, then they're rotating so fast that by the time the ball gets to the other end of the carousel, or the merry-go-round, they are there. They have rotated to the north position, and they are there to catch it. So they can catch it themselves. Right. It's kind of like how I kind of visualize it a little bit from the outside reference frame. Right. The inertial reference frame.
Okay, so that's the general conceptual picture of what's happening on a rotating reference frame. And there's ways to quantify it, but I don't want to get into that yet. But I do want to just talk about directions. So the first thing is to picture the merry-go-round rotating clockwise, let's say. You're looking at it from above with the camera, and the thing is rotating in a clockwise direction.
Right.
So say somebody at the bottom of it. I'm hesitant to use like north, south, east, west, because we're going to talk about those kinds of directions when we get into like picturing the globe.
Right.
But picture at the bottom of the circle, bottom of the merry-go-round as you're looking from above. The thing's rotating clockwise. The person at the bottom throws something to somebody else across from them. So throw something up in our view, looking from above. That ball is going to go in a straight line according to us looking from above. But the people are rotating clockwise. The person across from them, the second the ball is let go of and it's now in the air, the person's rotating from 12 o'clock to like 1 o'clock, 2 o'clock, 3 o'clock, right?
Right.
The ball, though, just went straight forward and hit where 12 o'clock, where the person was, which was at 12 o'clock, right?
Yes.
So what would the person who threw the ball see? Which way would the ball move according to them?
See, I work it out slightly differently. I imagine if you were the other person, so if the person is throwing it from 6 and you're the person at 12,
right?
You're going to see the ball veer to your right if you're the person at 12.
Yes.
This is kind of the way I picture it. So then I know the person that threw it, they're going to see it go to the left.
Okay, sure.
I don't know why that works out better in my head.
Right. Yeah, I get that. And I'm with you. I think both people would agree that they both understand that, right? But the basic curved path is if there was a line connecting 6 and 12 o'clock, the ball would curve to the left of that line.
Right.
Yeah.
And so I want to take a brief moment to add to that is, it seems like, okay, we kind of picked these special 6 and 12 spots. Mm-hmm. But if you put someone at 6 and 9, mm-hmm. you still see the same thing. It curves to the left.
Yes. If you threw a ball from 6 o'clock to 9 o'clock as the thing rotates clockwise, you would see the ball veer to the left of the path that you expected it to take. Like if the direction the ball's moving, you expect it to go that way, but it's like someone is sitting in the ball and takes a steering wheel controlling the ball and steers left. And that curves the ball to the left of that original path.
Yeah. So, but there's where you put any two people anywhere you want on this carousel, mm-hmm. and someone throws a ball to the other person, in their view, it curves to the left of the original path.
Right. And it I think what you're getting at is, you said it, any two places. It doesn't even have to be at the edges of these circles, right? It could be someone sitting like at the top of the 6 o'clock and the top of the, or like almost close to the center, right? And like the 5 o'clock line. It's still going to veer to the left in this rotating frame as something moves in any direction.
As long as we're spinning.
You can throw it from 1 o'clock to 4 o'clock. It doesn't matter. Always going to go left.
Yeah, and on the edge, near the middle, wherever. You pick anywhere on the disc, it'll go to the left, as long as you're spinning clockwise.
Yep, right. Yeah. And what does left mean? So if let's just quickly do the 12 o'clock throwing to 6 o'clock. Throw it downward, and now the person that was at 6 o'clock is rotating towards 7 o'clock, and the ball is going to look like it veered to the left, like it went towards the 5 o'clock direction. Even though it was headed towards the 6, according to you.
Yeah, so it's
still left.
You're always measuring with respect to the direction the ball was thrown in. So if the ball is traveling from 12 to 6, it's to the left along that line. If it's going from 6 to 12, it's to the left along that line. You know?
Right. Yeah. Right. So what is that effect called? What we're describing is the Coriolis effect. So it's an effect that a moving object experiences when it's moving through a rotating reference frame. So from the perspective of the rotating frame, there's this strange effect that looks like something's forcing the ball in some direction, but you can't really explain it. There's no like rockets on the thing to steer it. So what's causing that? It's because you're in a rotating reference frame. Right.
And I don't know if you want to talk about this at all, but I feel like a little like I want to get on a little soapbox. So yeah, we're talking about the Coriolis effect, or there's also the Coriolis force. When you're in this rotating frame, there's a force that's there. And as physicists, they have a few different names for this type of force. One of them is inertial force. Another one is pseudo force or fictitious force. And those last two, I'm not the biggest fan of those. Because if you've been in a car and you go in a circle really sharply, you make a really sharp turn, you experience a centrifugal force, which is also a fictitious force, but like that force is pretty real to you. Right. You know, in that I just feel like the choice of fictitious force gives like preference to a inertial frame versus a non-inertial frame.
Right.
But I don't know that you need to make that choice. I would go with a different name than a fictitious force.
Yeah. It's just representing the actions of something in your rotating reference frame. It's like those paradoxes. Like, it's not really a paradox. Everyone who understands physics can explain what's happening. Like, everyone agrees that this is what should happen, and it's not like wrong.
Right. And I guess like what I want to say is like if you were to replace the ball with yourself and you were thrown or you were running along the line, like you're going to experience that force. You'll feel that force.
Right. Yep. It's a real thing. Yeah. So let's tie this back into hurricanes. How does the Coriolis effect lead to hurricane motion? We talked about the low pressure of the hot air that rises up and it sucks in the air coming in from all the surrounding places. So think about the direction that air moves on like the Earth scale. The fact that the Earth is rotating, what direction is the air moving? So if the air is, say, close to the equator and it's moving towards the North Pole, which way is the Earth rotating now? We should probably talk about that. Is it a clockwise or a counterclockwise rotation as viewed from somebody above the North Pole, let's say?
Okay, above the North Pole, it is a counterclockwise rotation,
that's right.
I believe, because it goes...
East Coast sees the sun first, and then the West Coast sees it. So that, to me, thinking about the East Coast rotating around, would see from above the North Pole, you would see the Earth rotating counterclockwise.
Right.
Yep. So imagine a piece of air moving towards that low pressure zone from the equator to the low pressure zone. Is it moving like from 6 o'clock to 12 o'clock or 12 to 6? Like, what's the direction would we say? And actually, I need your help visualizing this, because I think I get it, but I need some concrete answers to like, what is the circle that we're describing as rotating? Because now it's not a disk like the merry-go-round, it's a sphere. So like what circle of rotation are we talking about here?
Right. Well, so that's kind of the neat part about it being a sphere, is in some respects you can reduce it to a circle, but in other respects you can't.
Right.
Because like the actual answer is, if you were at the equator and if there's a little bit of air right at the equator and it starts to move north, it will experience no Coriolis force.
Exactly. Perfect. I agree. Yeah, I think I said that actually, so I shouldn't have said it that way. But yes, you're right. You're right.
And that's because, not because we're on a disk anymore. It's because we're on a sphere. So there's actually a three-dimensional part of this that needs to be considered.
And I have a little bit of a hard time visualizing this for some reason. But yeah, I hear you. It's if something was on the equator, a piece of air on the equator, and moved towards the North Pole, that would be like on the merry-go-round, someone at 6 o'clock throwing the ball not towards 12 o'clock, but like throwing it out of the merry-go-round, like straight up towards the camera that's watching it from above, right?
Exactly.
So that's not the same thing. There are effects that describe that, but that's not this Coriolis effect that we're talking about.
Right. Well, yeah. So one kind of little trick you can do. I don't know if this will help. This might help our physics listeners out there. Is I'm gonna get little math just really quick.
Ooh, we're getting into some right-hand rules.
Yes.
Nice. Okay.
The force, the Coriolis force is 2 times the mass times the velocity vector, the direction that the object is moving in, times the rotational axis vector. Or sorry, not times, but cross. So it's a cross product of these two vectors. And so, just to say that really quick, it's 2mv cross omega. But that equation, that general form of it, should be familiar to you if you've taken an E&M class. If you replace 2m with q and omega with b, you get qv cross b, which is the magnetic force. So mathematically, these two forces behave the same way. And so if you can kind of picture, you can kind of replace the spinning part of it with a magnetic field, and you can kind of get an intuition for what's going to happen, like how things are going to move.
Huh. I don't think I've ever thought of it like that, but yeah, I guess it's a v cross some other vector. So so for Earth, which direction is that rotational vector?
So I think
you called it omega. Is that right?
Yeah.
Yeah. Like capital omega. Is usually how it's shown in books.
Yeah. So I think it would be from the South Pole to the North Pole.
Yeah. And it's not just a line from like connecting South and North Poles. It like everywhere on Earth, there's this omega vector like passing through the whole Earth. Like imagine a plate of like, I don't know why I'm thinking this. Imagine a plate of like spikes and nails like sticking up from this plate. And that's at the bottom of the South Pole. And those spikes and nails go all the way through the Earth towards the North Pole, like just like vertically straight up through Earth. All of those little spikes and nails are that omega vector. At every place on Earth, you have this omega vector passing through you that points in that direction.
Yeah. So like if you do have some intuition for is that, I forget whose force that is, Lorentz? Well, Lorentz has the whole force.
The Lorentz force? Yeah. I mean, sometimes people call the magnetic part Lorentz, but
yeah. If you have some intuition for that, you can kind of imagine that. So like in this case, this would be V moving in the same direction as the magnetic field.
Mm-hmm.
Therefore, there's no, the particle doesn't do anything.
Right. If you're standing at the equator watching the sunset, or let's say the sunrise, actually, that's easier. Standing at the equator watching the sunrise, and that spike of that omega vector, the rotational vector, is passing through you, which direction does it point?
Your left.
Yes, it's pointing straight, like directly to your left. So, left, if you're staying at the equator, is like turning and facing the North Pole. So if air started moving to the left and it's lined up exactly with that omega vector, those two vectors point in the same direction, which, if you know some math about vector products, that cross product is equal to 0 if they point in the same direction. So you get no effect when the velocity vector and the omega vector line up together.
Right.
Cool. Okay, so back to my question of what circle are we talking about? I imagine this like merry-go-round picture generated on the globe by taking slices of the globe. So like depending on what latitude you're at, take a slice of the Earth. Like at the equator, just cut the Earth in half right through the equator. That's one of your merry-go-round slices. And then travel up to a different latitude, take a nice slice all the way through the Earth. And those slices are getting smaller and smaller in circular size. As you get up to the North Pole, you get essentially 0 size, right?
Right.
That's the picture that I have of these merry-go-rounds. And yeah, they have kind of like their pivot point straight through the line that connects the South and North Pole. Like that's the rotational axis for these things.
So I can think of another way to talk about it.
Okay.
And I don't know which one's better, and I'm totally fine if we want to go with one over the other and just cut out the other one.
Mm-hmm.
But because it's a cross product, and the cross product is, I think the technical term is bilinear or linear. You can take, A plus B, that quantity, that vector sum, cross C is equal to A cross C plus B cross C. I don't want to get too into that, but essentially what that means is we can look at individual directions to try and figure these things out.
Yeah, I see what you're saying. We could break up, since we're kind of like the air that we're talking about moving along the surface of the Earth is kind of like not throwing the ball straight to the person from 6 o'clock to 12 o'clock, but kind of like up also, right?
Yeah, there's always kind of some upward
component
to it. And so, if we, or like maybe we can combine both of these things. What we talked about was, if you're standing at the North Pole, and you go up, that you throw the thing up, there's no Coriolis force.
Right.
So really any component of the vector that is up in that direction is not going to contribute to this. So we can really, I guess, only focus on the disks that we're talking about. Maybe that's what we need to say, is that there's a reason, we can just get rid of, we don't have to worry about the up part of it. We can only focus on the inward part.
Right. Inward or outward. Meaning
if we're moving along the line, a longitudinal line? Yeah, a longitudinal line.
I'm not positive about that. The longitudinal part.
if we're moving, in some direction that is not along one of those longitudinal lines, so like, let's say you're at the equator, you're facing north, and you turn 45 degrees, and you start going that way. Now there's another component that you have to talk about.
Right. Yeah. So we're basically taking these wind directions and like projecting or like smashing them down onto the disk slice that we're taking through the Earth. Like that's the picture we want to have in our head, because we want to get back to talking about the Coriolis force in terms of this kind of like merry-go-round picture. And our merry-go-round is just the size of these like Earth slices. So, not at the equator, because we said any air that's moving north or south from the equator doesn't experience a Coriolis force. Just like someone sitting at 6 o'clock on our merry-go-round and throwing a ball straight up towards the camera that's looking at the merry-go-round, there's no Coriolis force there. What we want to think about is taking a little bit of air that's off the equator slightly and is traveling towards the North Pole, if the low pressure area is just north of it, that thing is going to be deflected just like the ball was deflected. But the difference is, we said, looking from above, the Earth rotates in a counterclockwise direction, not clockwise like we first explained with the merry-go-round. So if we think about that, instead of being deflected to the left, we said, right? Is that correct? Then
yes.
we're deflecting things. The air is getting deflected to the right of the path that we would expect it to take.
Yeah, and you can just run back through the merry-go-round. Everything we said about the merry-go-round rotating clockwise, just reverse all that, think about it going counterclockwise, and you'll quickly just see that, everything moves to the right.
Mm-hmm. So what I want the listeners to visualize is to picture a like arrow that's like swooping off to the right, like just kind of like a, I don't know, like a hook pattern in football or something like that. Like you're moving forward, but then you kind of like veer to the right. That's what the air is doing, actually, in relation to this rotating Earth. It wants to go in a straight line, but the Earth under it is moving, so it looks like it's veering off to the right. Does that make sense?
Yeah, and there is a semi-intuitive way to think about that one as well.
Mm-hmm.
I don't know if we want to... I'm not the biggest fan of it, but we can talk about it. And it's essentially that, Derek talked about looking at different slices of the Earth at different latitudes.
Mm-hmm.
So like the equator slice, if you're on the edge of that, because we're always on the edge of these circles,
right?
If you're on the edge of that one, it's actually moving faster, right, than the one that is on the edge of a 30-degree latitude. Santa Barbara, I think, is somewhere around there.
Mm-hmm.
That one
right.
is actually moving slower because it's a smaller disk.
Right. The Earth, you gotta travel around a larger circumference of a circle at the equator in 24 hours that the Earth takes to go around, compared to somewhere at a more northern latitude. Like imagine being close to the North Pole. That circle that you got to go around in 24 hours is pretty tiny. So you're going to be going a lot more slowly than someone at the equator.
Right. But then, so if air is moving northward, just like the ball, like, I gotta try to think about how this.
So yeah, I got what you're saying.
You got it. Okay.
The Earth is moving more slowly. The surface of the Earth is moving more slowly as you travel more north. So if something's directed north, it left somewhere moving pretty fast, but then it's now traveling over parts of the globe that are moving more slowly. So it's like it gets ahead of that part of the Earth, because it's now like it was moving really fast, but now all of a sudden the stuff under it is moving more slowly. So it looks like the Earth beneath it is getting dragged behind. Or in other words, that thing that's moving, the air is what we're talking about, is actually getting ahead of the surface of the Earth.
Right. Yeah. So it's moving to the right.
Yeah. So that's another way to visualize what's happening. But it all works out the same way as talking about the merry-go-round. But yeah, the bottom line is something moving north gets deflected to the right in the counterclockwise rotation of the Earth. Something moving to the north is going to veer to the right. How about something moving from the North Pole? I mean, we're not talking about the North Pole actually, but like far from the equator, farther than that first piece of air we were talking about. It's getting sucked into that low pressure area, and it's traveling towards the equator now. So it's traveling south, we would say, right?
Right.
Along the surface of the globe. But projecting it onto that slice that's like the merry-go-round, it's as though it's moving away from the center of the circle, away from the center of the merry-go-round. So if something's moving away from the center of the merry-go-round as it's rotating counterclockwise, it's still, like we said before, everything looks like it gets deflected in the same direction from what you expect its path to be. So this thing, just like the other piece of air, this piece of air gets deflected to its right. So imagine a swooping arrow that starts, if you were to draw it, starts at the top of your paper. Draw your pen, drag your pen downward, and then swoop it off to the right of its original path, which means your pen actually goes to the left. Does that make sense to you?
Yep. Yeah.
So you're kind of like making like a J. That's the direction that air would travel on the surface of the Earth, moving towards the low pressure area.
Right. Yeah. And then, you can fill in the same thing from the east and from the west.
I'm glad you said that. Can you? Because I know that's what most of the books and pictures show. And I tried to like actually work it out with the vectors and everything. And I am not positive if they actually do that. So imagine a piece of air on the surface of the Earth to the left of that low pressure region, moving to the right. Like the air is moving directly east on the globe.
Right.
Does it veer off to the right like the other directions do? Which would mean it goes south? Like
yeah. So
I need help with that one. I need help with that one.
Imagine you're on the disc.
Mm-hmm.
And you're right at 12 o'clock.
Okay.
Is that because where you said we were throwing it? Which direction? To the east?
I originally said, moving to the east.
Yeah. Okay. So you're at 6 o'clock.
Okay. Good.
And you're facing the direction you're rotating, which is counterclockwise.
That's right. Counterclockwise now for the Earth. Yes.
Yeah. And you throw the ball straight in front of you.
Mm-hmm.
If you imagine that the ball is going to go straight, but you're going to see it, again, curve to the right.
I got it. But what does that mean? Like to the right, according to somebody at 6 o'clock on this rotating disc, like that means it leaves the merry-go-round, which it does. Like on the merry-go-round version of this, it veers off to the right. I got that. On the globe version of this, that means it goes... It's not like it just like rocket ships off the surface of the Earth. It does do that a little bit, but it moves south also. Is that right?
Yeah.
That's hard for me to visualize. I don't know why it's so hard for me to visualize, but it's true. Because I got a way to see it. It veers to the right, and there's another merry-go-round that's bigger than the merry-go-round you're on, and it's like it goes onto that merry-go-round. Does that make sense?
Yes, I think so.
That's the equivalent of going south. Like you're getting on the bigger merry-go-round, which is south of you.
Okay, well, all right. Okay, I'm still okay. Now I'm confused.
Okay.
Because I think you actually. I'm trying to imagine it moving directly east. And that might be the issue, is that we're on this like perfect line. Mm-hmm. But if it's directly east, I think it will move away from the Earth. And I think that's it.
So I'm imagining this is going to get a little bit more complicated. But imagine, like, this is not actually what it is, but imagine you're not on a merry-go-round, but you're on a rotating cone.
Okay.
And you're standing kind of in the middle of the height of the cone.
Okay.
So you throw something in the direction the cone's rotating. It's going to travel in a straight line to somebody watching this from the outside, which to your perspective, it veers off to the right. But there's more cone beneath you that's bigger in radius, right?
Right.
Like straight leaving the Earth, I would picture it like going perpendicular to the surface of the cone, which it's not. It's got a little bit of component like along
you're
the
totally
surface.
Right.
Yeah.
So if you're on the equator and you throw it directly east, it's going to want to leave the Earth. It's going to go up away from the ground.
That's right.
And that is it.
Yeah, there's nowhere else for it to go.
Right. But if you move upward north, then there's another component. This is why I was trying to like always work it out in components.
Right.
So there is a component that is going to move upwards, but now there's also a component that's going to make it move
Southwards, exactly.
Southbound.
Yeah. So I'm going to push back a little bit on that, in that I think it has more to do with the fact that there is Earth for it to travel over that is south of your position. Like if you're on the equator, I think it's the same, like it's a parallel vector. It's the same direction of motion. It's just there's no Earth to be over anymore except the equator Earth.
Okay, I might have to draw a picture real quick. Yeah, I'm understanding what you're saying.
Can I talk you through a drawing that I think would explain it? After you finish your drawing.
Yeah, let me... Yeah, okay, all right. Let's hear your drawing.
Draw a circle.
Sure.
And then draw a line tangent to that circle somewhere. Say 6 o'clock.
Okay.
So that is the equator. Like it would just leave that circle, right? And travel in the direction you're moving, but then also like eventually it looks like it's veering to the right of... See, this is where it's weird. It's like to the right, quote unquote, but it's like to the right, which is perpendicular to that circle, is directly like curving up, like away from the surface of the Earth, right? Like you on the surface of the Earth are veering from where you are right now, and somebody watching you from above, you're moving to the left in like this curved pattern, right? But the ball or whatever is moving in a straight line.
Right.
So put yourself in the perspective of the person on the rotating platform or on that circle. Okay. It looks like it veers to the right. But on the equator, what does that look like? That's leaving the Earth, like just straight going away. The altitude gets bigger and bigger and bigger. Nothing else happens. Right?
Right.
So now draw a circle that's bigger than the circle that you just drew.
Concentric.
Concentric, yes.
Okay.
So now imagine you threw the ball and it's traveling in the same direction. It's the same straight line perpendicular to that circle, but now there's that bigger circle that ball is over. So right. Where is that bigger circle on the globe? That's somewhere south of you. And you would say that ball is now over something that is south of where I am right now. Does that make sense?
Right. Yes.
Yeah. So on the equator, there is no bigger circle to be over, which you would say is south of you.
Right. Yeah. So it just moves away from the ground.
Yes. That's right. Okay. So we have our air that's getting sucked into this central low pressure area. It's low pressure because the warm air rises and it leaves this empty space behind. And so air comes in to fill that space. Every direction of moving towards that low pressure region on the counterclockwise rotation from looking from above is going to lead to the air being deflected, we said, to the right. Is that right?
Yes.
So imagine we have the air that's moving from the north to the south. We said that kind of made like a J path. Imagine the air from the south moving towards the north into that low pressure region. That's like a lowercase r kind of shape.
Right.
A badly drawn lowercase r. Put those two things kind of next to each other, like position the J slightly above the R. In between the J and the R is a little circle. You can imagine like a swoosh of air or a swoosh of like rotation that's happening by that moving air, right? Do you get what I'm saying?
Yeah.
So that right there, that's your hurricane. It's everything that's getting deflected right, and then you can draw the other ones also. Draw a straight line from the left to the right, and then have something deflect to the right of that line, of that original direction of motion. That adds to that kind of like circular motion of the rotation of that air. So then we have this big rotating collection of all this in-moving air, but then getting deflected because of the rotation of the Earth. That leads to the hurricane now, all this stormy air rotating which direction?
Going right. Going this way. So it is going to be moving counter, I think, clockwise.
Yeah.
Is that right?
Yeah, that's right. So all the rotations of storms and cyclones in the northern hemisphere, we haven't talked about the southern hemisphere yet, but we're talking about northern hemisphere, lead to counterclockwise rotations, all because of the Coriolis effect. Right.
All because we're on a rotating frame.
Yep.
We're in a rotating frame of reference.
Exactly. The Earth's rotation leads to these hurricane circular motions in our perspective. Right.
Right.
Okay. So that's the rotation of the hurricane. Now we have this like other stuff happening. There's the winds that just move the hurricane from off the coast of Africa into the like Caribbean and eastern United States, right? There's like ocean currents that like move the stuff around. We kind of deplete, the storm kind of depletes the energy of the surface waters of the ocean, and you're left with like kind of cooler water, and so the storm can't survive, so it's kind of like moving into warmer waters and keeps traveling with the warm water. That's one way to think of it. It's like collective motion. But all the while, we have
interesting.
This low pressure area, and it's sucking in this air, which just leads to this rotation because of the rotation of the Earth, leads to the rotation of the storm in a counterclockwise motion. And there's other stuff. I think you kind of mentioned it, and I think this is the last puzzle that I have left of like, I don't really understand it. So we talked about the incoming air getting sucked in to the low pressure region. It rises up because it's with all this other warm air. That's the evaporation off the ocean, right?
Right.
And then what happens when the air gets up to the highest point, like the highest of the high part of the hurricane? Where does it go?
I think it moves back out away from the eye of the hurricane.
It does, right? So that's what I thought. But then what that means, I think what that means, and correct me if I'm wrong, now we have stuff moving the other direction. Like, imagine the low pressure region, but then a piece of air moving back from that low pressure region to the south.
Right.
It's going to get deflected to the right of its direction of motion. Correct?
Mm-hmm. Yeah.
Is that in the opposite direction as the air on the surface of the Earth at the bottom of the hurricane, which is getting deflected to its right?
Right. Okay. So yeah, let's think about that. So you have, if air's coming in from the east, it's going to get deflected, or going from west to east, it's going to get deflected right, which is southward. Mm-hmm. But then you have at the top, we think, air going the opposite direction. So it's going to go from east to west. It's going to get deflected to the right, which is northward.
Right. So does that mean we have like a twisting, like the top of the hurricane is rotating in the opposite direction as the bottom of the hurricane?
I think slightly not. This is just intuition. I haven't thought too much about it yet, but I'm imagining, okay, let me draw a picture. It's going to go to the right. Because because I was imagining, the thing I'm trying to get at is, it's a divergence sort of thing. Mm-hmm. Like all the air is coming, it's sinking on the lower bottom part. It's sinking to the hurricane. It's all flowing inwards towards the eye, but outwards, if it's all flowing away, I don't know if the net result is that it ends up combining to
like a collective motion
to do anything.
Yeah. I see what you're saying. I could see that.
But
yeah, you're right. Yeah, like what does that even look like? Like not. Oh God, I drew a bunch of right angle kind of arrows, and now I have a swastika on my paper. I'm gonna add a few more. Like they definitely all move in the same direction, which is clockwise, but it's not like I see what you're saying. They're not collectively making this like huge rotational like movement that like causes the whole thing to move, right? Like yeah, it's like it's getting we can say it's like dispersing the air rather than what's happening at the surface of the earth, which is the air is coming in together and it's like building up this motion. Like
it all kind of like adds together to make a circle. But then when it's all going away, it just goes. I don't see like a circle forming really,
right?
At least not, and maybe it does, but if it is, I think it'd be a larger circle.
And I mean, I don't have. There's no like physical reason that I can think of why this is true, but my picture of it in my head is that the winds are kind of slower. Like the outward moving air is slower at the top of the hurricane than the inward moving air at the bottom of the hurricane, like at the surface of the earth. I don't know if that's true. I don't have any reason for that to be true, but it feels correct.
Right. And so do we have a reason why we think it is moving away from the eye of the hurricane at the top?
I don't, except for just like where else would it go? Like we got air coming in from below, and I think it rises up to the place where it's like in thermal equilibrium somewhat with like at least the densities are the same, right? It's going to rise until the densities equal to the surrounding air. And then it's not going to rise any further, so it can't really expand up anymore. So it kind of gets trapped and just has to spread out sideways. That's my guess.
What I'm kind of wondering is, do you get a high pressure zone near the top of the hurricane then?
I don't know. Higher than what? Higher than
I guess the bottom or the surrounding part.
I don't know. You mean because there's just more air there? Is that what you mean? Like
it's kind of because it's all moving.
It's like building up
to that one spot. I don't know.
The last part that we haven't talked about is it falls back down. Like it spreads out, but then it gets sucked back like down. Like it cools off, which means it gets denser, and then it falls back to the surface, and it's kind of like this churning cycle. Outside of the rotation of the hurricane, but like looking at a slice through the hurricane, like you're cutting a slice of cake, there's these like other cycles that are happening.
Yeah. If you if you were looking at a hurricane and you cut it in half vertically, you'd see, the eye is kind of a dead zone, but on the edges, there's, at the edge of the eye, there's air going up, like we said, and then at the top it goes out, and then once it's far away it comes back down, and then once it gets to the surface of the ocean it goes back in, and you kind of get these two loops that will form.
Yeah, we haven't talked about
that's a little simplistic, but that's roughly.
Yeah, we haven't talked about the eye, but what's happening there? Why doesn't everything just spiral? Like why doesn't it actually reach in like at one point and then everything just go up? Like why does the eye even exist? Why is it clear? I don't really understand why the eye is a thing.
I don't know.
There has to be a place where the air is rising, right? And that's that low pressure area. But like, why does that keep the eye clear?
Right. So I'm wondering if it's almost like a. I'm wondering if you could think about it in a centrifugal force way. If you have things spinning, it doesn't want to shrink; it wants to get bigger. And so I'm wondering if that might be
it's just moving too
that.
fast, close to the center there, and it kind of gets flung outward. Like there's like a balance of like the low pressure sucking it in, and then the outward like rotational force pushing it out, and we're left with this like perfect balance. That's interesting. Maybe.
Yeah. Yeah, I know that there are winds in the eye, but it's very, very
much calmer
compared to
right.
Yeah,
and the wall of the eye is the stormiest, like the strongest winds, which you can kind of picture. Like that stuff's getting sucked in, and it's like it's at the like hook of the J that's driving that thing sideways the most when it gets closer and closer to the low pressure area, right? So we got high winds at the wall of the eye, and then it's just maybe we're thinking it's just the air is getting flung out because it's rotating so fast there that it can't come in any closer. And then you're left with this clear eye of the hurricane. Cool. Well, I got one more question for you, and then a little closing remark.
Okay. All right. Yep. Sounds good.
You said the equation for the Coriolis effect is 2 omega cross V, or V cross omega, depending on which one you're considering.
2m.
Oh, the force. Yes. The force has the m. You could talk about acceleration, Coriolis acceleration without the m, but yes.
Yeah, I guess.
But my question is, what's up with that 2? That seems weird to just like have a 2. Why is it 2? I have a little bit of an answer, but I didn't know if you had an actual answer.
So I think the mathematical reason behind it is that it's a second derivative.
Yeah, it's an acceleration of something.
And so I think you have let me. Okay, I think you have a square somewhere in there, and then that ends up pulling you down to a 2. I think, and that might not be a great answer, but
it'd have to be. It would have to be the position as a function of time would have to be something that goes with time to the second power, because you take 2 derivatives to get the acceleration of the 2 derivatives of the position with respect to time gives you the acceleration. So you need time squared somewhere, and then taking 1 derivative will bring down the 2. Taking a second derivative you'd still have your 2's hang around, right?
Oh, nope, that's not where the mathematical part of it comes from.
Okay,
actually.
I would have been kind of surprised if that was actually what it was.
Yeah, no, it comes from mathematically. It comes from grouping 2 terms together. So when you take a derivative of a vector in a rotating frame, you get the derivative of that in an inertial frame times omega cross the vector, plus omega cross the vector.
Okay.
So yeah, a derivative in a spinning frame, a rotating frame, is just the normal derivative plus the cross product of the rotational axis and the vector itself. And so since you do 2 derivatives of position, you get 2 omega cross r's. That's the mathematical reason. They add together.
Huh. But the like centrifugal acceleration or effect, there's no 2.
Or sorry, not r, but
it's so Coriolis is 2 omega cross v. Like it's a 2, but then you have an omega and a velocity vector. But then in the centrifugal effect, there's no 2, but it's 1 omega crossed with another omega crossed with position.
Right.
So why isn't there a 2 for that one?
So that's a product rule thing. Is what's happening. So when you take I don't know if there's a great way to talk about this, but if you imagine what I said, it's the regular. We can just say it's the rotational velocity. That's not the right word. The velocity in the rotational frame is equal to the velocity in the inertial frame plus the position crossed with it's the other way around. The rotational axis crossed with the position.
Okay.
Okay.
Yeah.
Then you take another derivative of that in the rotational frame. So now you're looking at acceleration. but that second derivative has to get applied to both of those terms. It has to get applied to the normal velocity, and then also it has to get applied to the omega cross r term. And so the omega cross r forms its own vector. So when you get, that's where you get the omega cross r, is because instead of having omega cross position, now you have omega cross that vector, omega cross r.
Right.
So that gives you the centrifugal force. And then when you apply this to the r term, you get the velocity now, but you get that it happens twice, and so they sum together, and you get this 2.
And therefore 2. Yeah. Got it. I kind of got it. So I definitely have derived all of these at some point in my physics career, and it's like, this is like maybe one class per semester of classical mechanics that you take that you're like exposed to this, and then you never touch it again. So it's definitely not something that I've had a ton of practice with, but I do remember driving these things from like first principles. And I remember liking it too. It was pretty fun, but then you just touch it once and then that's it. You're like done. Like,
and I'm just looking at Taylor right now.
Oh, that's Taylor. Okay, good.
That's where this is coming from.
Got it. Yeah. I used Goldstein, but I never had Taylor as a book.
But does Taylor make the great cover photo, Joe?
Is this the classical mechanic book?
Yeah.
Yeah. The classic car.
Yeah.
Oh, Goldstein was grad school. What was my undergrad book? Thornton Marion, pretty sure. Taylor's an undergrad book, right?
I had it for undergrad.
Yeah.
I think it's designed for that. So, I mean, if you have a better reason why there's a 2, because that's just a purely mathematical, like, hey, I can take derivatives.
So I read a quick explanation from a website that looked like it was built with like, HTML from the 90s, which sometimes has like amazing information and oftentimes just has terrible information. So I don't know how valid this is, but it said that Coriolis, when he was working this out, approached it from an energy perspective, and he considered both linear and rotational energies, and they both lead to an omega cross v term. And so you add both the linear and the angular energy parts, and you get a 2. But yeah, who knows if that's actually correct.
Sorry, can you say that one more time?
There were 2 types of. So when Coriolis was deriving his effect, he was approaching it from the perspective of energy, and so he worked out both linear and rotational energy types. And when you consider both of those, they each contribute their own terms, and you get this factor of 2 because each one of them is doing something for the Coriolis effect. And the
Gotcha.
website I read said other people, meteorologists, tried to work this out on their own, and they could never get that 2 to show up. And it was explained that they couldn't get the 2 because they weren't considering linear, I think, the linear part of things. And so there's still like a linear motion happening in the rotating frame in addition to the rotational part. But that's such a hand wavy argument. First of all, we are talking about accelerations and forces, and that website was saying it came from energies. I would have been more comfortable if it said linear and angular momentum, but it didn't.
Right.
Why are they exactly the same contribution? Like, why does linear give you an omega cross v and rotational give you the exact same thing of omega cross v? So I don't know. That's what I read. Who knows? It's the internet.
I'd have to actually sit down and think about the math to see if I could make sense of that.
Right.
I mean, I was trying to think if omega v means anything to me. Omega times v, and I think omega is v over r. Is that right?
Yeah, that's one way to think of it. So, I mean, it's your v squared over r. But all of these are, I mean, they're all accelerations. So like dimensionally, they're going to work out to a v squared over r or an omega squared r.
Yeah.
But, okay. So to wrap up, one thing we haven't discussed is what's going on in the southern hemisphere. So, we talked about it a little bit, but how would you visualize hurricanes rotating in the opposite direction when you're south of the equator? Like, what's the change that happens? Because the Earth isn't changing its direction rotation. It's still, the sun still rises in the east for people in the southern hemisphere. So what's going on there?
That's a good question that I was not able to intuit because, if you, I think it was in Taylor, he's just saying, okay, well, yeah, you look at the southern hemisphere from the south.
Right.
But so if you do that, now the Earth is spinning clockwise, but why?
So I think the way to think of it is something moving away from the equator, like a piece of air moving away from the equator in the northern hemisphere. Imagine the merry-go-round again. Is it moving towards the center or away from the center?
Away.
There's a piece of air moving north in the northern hemisphere.
Oh, north. It's towards the center.
It's moving towards the center of the merry-go-round, right?
Right.
Now imagine the same piece of air in the southern hemisphere moving north.
It's moving away.
It's moving away from the center, right?
Yes.
So that right there, I think, gets you the opposite direction of deflection in a way.
Yeah.
The other way to think of it is, you're looking at it from below, which then is rotating clockwise, right? But that doesn't really explain it because you could have looked at the merry-go-round from underneath it. And
right. Well, let's flush that out a little more really quick.
Okay.
So okay, we're gonna keep our view from the north.
Mm-hmm.
Okay, then like you said, the piece of air in the southern hemisphere moving north is moving away. So
away from away from what we're saying away from is away from the axis of rotation, the line straight through the merry-go-round's middle, or on the Earth, the line that connects the North and South Pole. That piece of air is moving in multiple directions, but the one we care about is it moving towards or away from the center of that circle, that merry-go-round slice. And it's in the southern hemisphere, when the air is moving north towards the equator now, it's moving away from the center. It's getting into a merry-go-round that's bigger than the one it was just in, right?
Yeah. Yeah. Sorry, I was drawing.
Yeah.
Yeah. So the thing I want to see if it works for this is if we're looking at it from the North Pole, and everything is still spinning counterclockwise
from the North Pole, right?
Yeah. So like we said,
looking from above the Earth, above the North Pole. Yep.
Yeah. So everything is going to still be deflecting to the right.
Yes, from that view. And so a piece of air moving to the north in the southern hemisphere is moving away from the center, and it's getting deflected to the right, which, according to somebody on the surface of the Earth of the southern hemisphere, like if you were to draw that on the map of the Earth, to the right as it moves to the north. Wait, is this correct? Or am I saying it wrong now?
So as it moves north to the right,
I think I just tricked myself. It is to the right, but when we were in the northern hemisphere and we looked at a piece of air moving north and we said it was deflected to the right, that was deflected from its original path. It was deflected to the right, which is east. Correct. That's that R shape that we got for the piece of air moving north. Now, This piece of air is in the southern hemisphere moving towards the equator, moving north. What I'm picturing and the way I worked it out in my head is imagine the direction that it's moving is like, I don't know why this makes sense in my head, but maybe it does to you also. Picture the globe sitting on a table, and the globe is enormous, like the size of a building.
Okay.
So it's not sitting on a table, it's sitting on the ground.
I was, that's a big table.
It's sitting on the ground. It's a huge globe, but it's sitting on the ground.
Okay.
It's the size of a house. You are standing on the ground underneath this globe, like kind of tucked, like wedged into this, like where the globe meets the ground, right? And you're looking at stuff happening on the globe.
Right.
There's wind. There's something moving from within the southern hemisphere. It's moving towards the equator. It's moving north.
Right.
So the reason I wanted to get this picture is imagine like with your pen holding your pen pointed in the direction that the air is moving. It's kind of like moving from in front of your chest to like up over your head behind you. Does that make sense?
Yeah.
Like that's the direction that I'm picturing, which if it was to deflect to the right, why is this so hard? It's so hard because it's like a 3D picture. Oh, I just solved it. I just figured out what the problem is. Take your pen. Remember, we're projecting the direction of motion onto a merry-go-round, like a flat slice through the globe, right?
Right.
This pen is showing you the direction that the air is moving. Project that horizontally. So if the pen started in front of your chest and like rocket shipped above your head, that's the direction the air is moving.
Mm-hmm.
Start with the pen in front of your chest and then project it down onto a horizontal surface. It's pointed down straight at your chest. Not up, not down, straight at your chest.
Right.
Is that right?
Yep.
So it's moving away from the center and it's deflected to the right. Which way is that? Is that east or is that west?
No, it's west.
It's west. So a piece of air moving north in the southern hemisphere, moving towards the equator, moving north is going to get deflected to the west. Whereas when we were in the northern hemisphere, a piece of air moving to the north, away from the equator there, it's deflected to the east.
Yeah, I think that is a much better way to think about it.
Yeah.
Personally, because it's when I in videos that I saw or in books, I just saw it. We'll look at it from the southern pole now, you know.
Right, but you could have done that with the merry-go-round. Like, why did that make a difference?
Yeah. Like, why pick that direction, right?
Right. Right.
Yeah. So I think your way makes more sense.
Yeah, it's definitely correct, and it's definitely like, I don't know, all-encompassing, but it's harder to explain for sure. I don't know why I needed the globe to be the size of a house, but that's like the second I did that, then I've pictured the pen showing the direction of the motion. I'm holding a pen in front of me, and then it became really clear.
Right. Maybe another way to think about it is like imagine the sun's directly above you,
mm-hmm.
and you lean forward. That would be indicative of you being on the northern hemisphere, going north. You lean forward. Your shadow is directly in front of you. But then now if you lean backwards, that'd be like you standing on the South Pole. Standing in the southern hemisphere. Mm-hmm. Now your shadow's going the opposite direction, 180 degrees. It's going behind you. So the projection onto a horizontal plane is opposite directions.
Right. That's correct. Yep. Yeah, we're always projecting it onto this flat merry-go-round. And that projection leads to the direction in our east-west coordinates of a piece of air moving north changing.
Right.
And we should be able to do the same thing for a piece of air moving south away from the equator and see that it gets deflected. So if it's moving south, I have my pen in front of my chest again and it's moving south. It's kind of pointed like towards the ground in front of my feet if I was standing up.
Mm-hmm.
And I'm projecting that now flat. So I'm laying my pen horizontally and it's deflected. We said
to the right.
To the right.
Deflected to the right.
To the right, which is to the east. Now back, like moving back towards our globe, to the right is something east.
Right.
Yep.
So something moving south gets deflected to the east.
In the southern hemisphere.
Right. Yes.
Right. And I'm going to leave it as an exercise for the reader to do the east and west moving airs in the southern hemisphere.
Right. Yeah. The cheat, the thing that like we've kind of mentioned but haven't really stated, is this is exactly equivalent to you looking at it, looking at the Earth from the South Pole and realizing it's spinning clockwise now.
Right. Right.
I'm sure like there's a mathematical, I haven't derived it, but it's mathematically equivalent to what we're saying, but it doesn't make physical sense to us why you would do that. So
I just thought of something. I think it's kind of cool. I don't know if it's true. I think it is. Imagine you have a globe, like a normal size globe now, and you have a toilet paper, or let's use a paper towel, like the cardboard paper towel thing, something kind of long and cylindrical. Drill that through the globe. I don't know what the globe's made out of, something that cardboard can cut through, but you have a cylinder now, like piercing through the globe, right?
Okay, right.
And we're saying that in the northern hemisphere, hurricanes rotate counterclockwise, right?
Yes.
So take that.
Wait, in which hemisphere?
The northern hemisphere.
Yes.
Hurricanes rotate counterclockwise. Take that paper towel roll and rotate it counterclockwise from looking from above, right? You got that picture?
Yeah. Yes, so but I want to add, before we go too much further, I see where this is going. This paper towel that you've drilled through the thing, don't put it on the axis. Put it somewhere else. Yeah, like 45 degrees or something from the North Pole and the equator.
Right. Imagine the paper towel, between, I don't know, going, I don't know what,
straight through
I don't know
Arizona.
the geometry. Yeah, through Arizona and then coming out the southern hemisphere, and I don't know what's there. Maybe Peru, maybe like Chile or something like that. I don't actually know, but like like that, right? So have something rotating counterclockwise in Arizona on the surface of the Earth, like by rotating the paper towel roll, right?
Right.
Counterclockwise. What does that look like on the southern hemisphere? The paper towel's rotating the same way. It's pierced all the way through the Earth. And what direction is that rotation on the surface of the Earth in Chile?
It's the opposite.
It's the opposite, right? So it's the same thing we're projecting onto this merry-go-round. The problem is the surface of the Earth is like curved the other way.
Right.
That's why it looks like it's rotating the opposite direction. That's kind of cool. I've never thought of it that way, but I like it.
I hope that I like it too. I think that's a good thought process, and I think that's like a good reason why you can just imagine the Earth spinning the opposite direction if you look from the South Pole. Right. But I still like thinking about it the hard way. I think it makes more physical sense to me. Seems less arbitrary.
Right. Yeah, doing all the projections and thinking right-hand rules and stuff like that. Yep.
And so I think there's one more thing we're going to leave out, but you could read about it if you're an interested listener, or maybe we'll talk about it another time. But apparently hurricanes are one of the most efficient engines that we know about.
I saw that too.
Meaning the most efficient engine you can make is a Carnot cycle engine. And hurricanes are very close to the Carnot cycle.
Yeah. So going in a cycle from hot and cold temperatures and different pressures, and the whole cycle of the water evaporating and then condensing, rising, cooling, all that stuff. The thermal process that happens within a hurricane is pretty much as efficient of a heat engine as you get, turning that thermal energy into work, causing the winds.
Destroying houses.
Mm-hmm. Well, it's pretty nice too. I saw that on a video or read it somewhere, but it's that leads to some pretty simple thermodynamics calculations that meteorologists can make about like how much wind speeds there are going to be and like stuff like that. Like they could just directly calculate from the difference in temperatures and the waters and the air and stuff like that, and get a pretty good estimate of like what's going to happen because we understand Carnot engines so well, like in a physics and engineering perspective, like the calculations are pretty straightforward because of that.
That's pretty cool, especially when like you think like Carnot did this in 1824.
Mm-hmm. Yeah. Cool. I like it. So yeah, that's our physics of hurricanes talk, which took us interesting places. But hurricanes spin one direction in the northern hemisphere and the opposite direction in the southern hemisphere.
Cool.
And yeah, it's all about Coriolis effect and driven by some thermal differences, hot water on the surface of the oceans. And also, we didn't say this, but at the equator, we don't get hurricanes. And we said it in so many ways that the Coriolis effect is 0 at the equator, but we don't see hurricanes at the equator. They have to start a little further away and to the like where the Coriolis effect kicks in.
Right. Cool. All right. Well, if you liked that, tell your friends about this podcast.
Sure. Yeah. Or hit up thehyperfine.com or see us on Reddit at r/thehyperfine.
I think what are the things we're supposed to say? Like, share, subscribe.
I don't know. I bet everyone stopped listening now because this is when I stopped listening to podcasts or whatever.
Right.
YouTube videos. Smash that subscribe button, that like button. Like, nope. X, close the tab.
Right. And then tweet me at @SPLEZAC.
Yep. I am at like tortilla.
Especially if you have things you want us to talk about.
Yep, for sure. All right. I will see you soon, Zach.
All right.
Take care.
Have a good one.
You too.